In the previous classes we have seen the different mechanical compressors which can be used for hydrogen compression. We have also noticed that they have several disadvantages, like they have many moving parts, as such there is lot of vibration, noise being created. At the same time these systems are quite complex and bulky, require a larger footprint area. They have a high energy consumption, and it is very difficult to get the heat transfer being done using in these compressors. However, another option could be use of non-mechanical compressor, and these non-mechanical compressors as against the mechanical compressors have advantage that they do not have moving parts, and as such the operation is quite very quiet, it is noise free. At the same time the OPEX, the operation and maintenance cost in such non-mechanical compressor is comparatively lower. The design of these compressors is simple, they are more compact. Even some of the compressors which are thermally driven compressors, the energy input which is required for the compression process can come from the waste industrial heat. So, in today's class we will start with looking at the non-mechanical compressors. The first of this type is a cryogenic compression. Now, in cryogenic compression, this is actually a combination of hydrogen liquefaction and compression, and as such there are benefits of both liquefaction and compressed storage of hydrogen. At the same time there are challenges also associated with both the processes. Now, in this method, instead of compressing gas at ambient temperature to higher pressure, liquefied hydrogen is pressurized and then it is stored in a cryo compressed tank. So, again the cryo compressed tank has to hold higher pressure, at the same time liquid hydrogen temperatures. So, in this particular method the amount of fuel that can be stored is 2 to 3 times more than it could be stored at ambient temperature in a compressed gas. For example, if at 75 MPa we need to store about say 4.1 kg of hydrogen, and that requires say 100 liters at room temperature. In that case, if we reduce the temperature of the gas to 77 Kelvin, so the same volume, same amount we can store at a reduced pressure of 15 MPa. So, as such the volumetric density improves when it is a cryocompressed method of storage. However, the cryogenic compression, this involves technologically sophisticated modular elements, and these are sequentially connected, like there will be a liquid hydrogen storage tank which is connected by means of an vacuum insulated piping to a cryogenic pump. Now, all these accessories, the containers needs to be well insulated so that there should not be any heat inflow from the surroundings into the system. And as and when there is a requirement of hydrogen, it can pass through a vaporizer or an evaporator, and downstream we can get a high pressure hydrogen. But this method, this has volumetric efficiency which is twice as high as a mechanical compressor. The major challenge that remains with this cryogenic compression method is that we have to continuously monitor the thermal insulation, and this is because the holding temperatures are low and there should not be a heat inflow into the system. Also, the performance of such systems, that depends upon the geometry as well as the vessel material which we have used. So, insulation, compression, both the phases of the compressed gas and the liquid are stored, as such the geometry and the material matters here in cryogenic compression. Now there has been several advancement in the whole process of compression, like the inner composite tank, its liner, its thickness has reduced over a period of time. Then the use of lighter density alloys like aluminium as a shell material, that also improves onto the gravimetric capacity, like with aluminium alloy it is 9.2 weight percent. Besides, if say for example we are using a 50 MPa cryogenic cryo-compressed tank, then it is observed that as against the compressed hydrogen tank, the improvement in gravimetric capacity of about 91% is observed. At the same time, the mass of carbon fiber and composite which is required for such tanks in a compressed hydrogen tank reduces by about 46% and cost reduces by 21%. So, that is an advantage of storing in a cryo-compressed form. Now, the use of cryo-compressed vessels that has already been demonstrated in different automotive applications. There have been several prototypes already being demonstrated, like there have been hybrids like by Toyota Pyrus and BMW. Now, there are different advantages of cryogenic compression. It not only ensures higher volumetric efficiency, but higher energy density, at the same time higher gravimetric and volumetric capacities. But the major disadvantages are, since there is a requirement of low temperature, as such the process is cost intensive as well as energy intensive. At the same time, continuous monitoring of the thermal insulation is required. Since we need to liquefy hydrogen, as such the cost of liquefaction adds up to the process, and the biggest challenge is the vacuum stability. So, if it is desirable a 10 years of vacuum stability, that is very difficult to attain. The reason being, usually these vacuum stability is obtained when it is a metal which is being baked for a higher temperature, but here we are using a composite tank. Now there, if we look at the status, Lind is well known for manufacturing such cryo compressed containers, and they have already manufactured like with a pressure output which we can get of 35 to 90 MPa for flow rates of higher than even 1000 normal meter cube per hour, and these have been used at hydrogen refueling stations to fill fuel cell electric vehicles. So, this is one of the non-mechanical type of compression. The another non-mechanical type of hydrogen compressors are metal hydride compressors. Now, these are thermally driven devices. They are like the thermal absorption type of compressors, and in them the heat energy is converted into gas energy. So, basically the driving reaction is a metal, which could be a metal or an alloy, or it can be an intermetallic compound. It reacts with hydrogen to form metal hydride, and heat is evolved in the process. So, this forward reaction is an exothermic reaction. However, when the required heat is supplied to the metal hydride, the reverse reaction of desorption occurs, wherein we get the hydrogen back. So, this is a reversible reaction, and the advantage of this reaction is that the reaction is highly volumetrically efficient. So, we can store large quantities of hydrogen in these metal hydrides, roughly like if it could be even 100 grams per liter, and the storage of this hydrogen or the hydrogen gets into the metal hydride crystal structure, occupying the place inside the crystal. This method is quite safe in storage. The reason being, if there is a leak in case of any accident, then the reversible reaction, we know it is a endothermic reaction. So, for the release of hydrogen, certain amount of heat has to be provided. So, even if in case of a leak there is a hydrogen evolution taking place, with time the temperature of the system will drop, and that will reduce the rate of hydrogen evolution, and as such it is a safe method. Now, in this reaction, the major the most important component in the metal hydride based compressors is the metal hydride itself, and it depends upon the characteristics of the metal hydride, the compression, like the characteristics like what is its gravimetric and volumetric capacity. It also depends on the kinetics of the of this reaction, it depends upon the thermodynamics of the process, it depends upon the thermal conductivity of these metal hydrides. Now we will study much more detail about these type of hydrides when we will study the solid state storage of hydrogen. Here we will just look at some of the fundamentals which are essential to know when we study these type of compressors. Now to understand some of the fundamentals related to these metal hydrides, if we see this reaction, reversible reaction, in that case the equilibrium of this reaction is interrelated to the pressure, the composition, the concentration of hydrogen in the solid phase and the temperature, and this is represented by a pressure composition temperature diagram, PCT diagram. Now if we plot a PCT diagram wherein we can plot the pressure, composition at a particular temperature, we will get curves. So these curves, this is at a temperature T. Now if we see this curve, there is a region which is flat, this region which is flat, this is also known as plateau region, and different metal hydrides may have different this plateau pressure at different temperatures. So in fact this PCT is a characteristic of specific metal hydrides, of different metal hydrides, they have different pressure, equilibrium pressures at different temperatures, and that depends upon the interaction of these hydrides with or these metals with the hydrogen. Now we can get different equilibrium, this pressure is the equilibrium pressure, the plateau pressure, and this can be different at a particular temperature for different metal hydrides. Now if there are low pressure alloys, in that case for them the pressure of desorption or the higher pressure can be less than 200 bar, and that is at temperatures less than 150 degree centigrade. Now such metal hydrides which have this characteristic of a desorption pressure of less than 200 bar or at temperatures of 150 degree centigrade, these are commonly the AB5 type of metal hydrides. So A and B we will see in more detail in solid state storage that these are different metals which have either a higher hydriding tendency or a lower hydriding tendency. There can be even high pressure alloys where the pressure can be as high as 1 kilobar, and under this category comes the alloys AB2 type of alloys, intermetallics. Now using these different metal hydrides we can get a compression ratio like the higher pressure to the lower pressure ratio. Let us say if the starting temperature is 25 degree centigrade, the lower temperature is 25 degree centigrade, and it is raised to a temperature of 100 to 150 degree centigrade, we can even achieve pressures of 10 to 50, but this is when the higher pressure is only 100 atmosphere. Now as this desorption pressure or pH increases, the compression ratio also decreases, and for higher pressures this compression ratio that can be achieved is 5 to 10. Now there are different factors which govern this compression process, like the factors which govern is the plateau slope. So this is an ideal curve which is showing a flat plateau, however this may not be flat in the real cases for different hydrides. There are some hydrides which may have a sloping plateau, so this plateau may have a slope. So the major factors on which this compression efficiency depends is the slope of the plateau, how much is the width of this plateau, that will decide on to the reversible storage capacity of these metal hydrides, how much amount of hydrogen they can take reversibly. At the same time there may be hysteresis. So if this is the absorption curve, then a desorption curve may be different. So it may not return back into on the same path, rather the absorption curve may be different from the desorption curve. So the absorption pressure usually it is higher than the desorption pressure, giving rise to a hysteresis. So in all these three parameters also the equilibrium pressure, the compression efficiency depends on. Now the major requirement when we select a particular metal hydride, as mentioned, this is the most important component of the hydrogen compression in the metal hydride based compressors. So the requirement in terms of the metal hydride when we select a particular metal hydride is that its pressure composition temperature curves, these should be tunable, so that we can achieve the desired compression ratio when the temperature is changed from TL to TH. At the same time they should have a high reversible capacity, they should have fast kinetics, faster absorption and desorption, and that could lead to higher productivities. They should have a lower plateau slope, lower hysteresis, good cyclic stability, they should be operational for large number of cycles. The material should be tolerant towards impurities. So, these impurities can be present in the hydrogen gas, and it should not change its characteristic when subjected to these impurities, or its performance should not degrade in the presence of these impurities, that is under idealistic condition required. The materials that are used should be scalable and of low cost. So, these are the desired properties of the metal hydrides which can be used for hydrogen compression application. Now, if we look at the metal hydride compressor, then in case of an ideal metal hydride compressor cycles, it need to have different processes. Now, if we draw it on a TS plot, let us say the higher temperature TH, the lower temperature TL, then we can represent it by a process. Let us say these are the isobars. If we draw a TS diagram for the compression cycle, considering it an ideal cycle, so starting from point 1 to point 2, this is an isobaric isothermal absorption by the metal hydride taking place from at a temperature which is TL and pressure PL. So, this is an isobaric isothermal absorption taking place when the system moves from state 1 to state 2. So, this is absorption. Now, then there occurs a polytropic process, that is the heating process, wherein the system moves from 2 to 3, and this is the heating which is done from TL, and the temperature rises from TL to TH in the process from 2 to 3. Now, the third step involves an isobaric and isothermal desorption. At this point T to T3 to 4, there occurs an isobaric isothermal desorption at a temperature of TH at a pressure of pH, and the process is represented by 3 to 4. And finally, there is a polytropic cooling that occurs from point 4 to 5 and then to 1. So, herein this polytropic cooling from TH to TL, and then isobaric cooling of high pressure hydrogen occurs from pH, point pH, and from temperature TH to TL. So, this is a step 4, 5 and 1. So, this is a cycle, compression cycle being represented on a TS plot. The same we can represent on a PCT curve, on a pressure composition isotherm. Let us say we have two different isotherms. So, the lower TL temperature, higher temperature is TH, and in this process ln of P is being plotted here. So, in the entire process from point 1 to point 2, this is an absorption that is going to take place. In the metal hydride, hydrogen is being absorbed, this is the minimum and this is the maximum concentration. So, in the absorption process, as the system absorbs hydrogen and it moves from the state 1 to state 2 at a temperature of TL and at a pressure of PL. At point 2, there is heating of the metal hydride bed so that its temperature rises from TL to TH, and this results into the compression of hydrogen and it reaches a pressure of pH. So, now the pressure pH is attained at point 3, then the discharge occurs at a temperature TH and pressure pH. So, this is absorption 1 to 2, then heating to take its temperature from TL to TH, then there is desorption from 3 to 4 or discharge or delivery at temperature TH and pressure pH, and finally it is cooled from point 4 to point 1 so that its temperature falls back to its initial temperature TL. So, TH to TL 4 to 1 step, this is cooling. So, this is a single stage compressor, a pressure composition isotherm demonstrated in a pressure composition isotherm. So, there are 4 steps involved: in absorption of hydrogen, then when it is heated, then the pressure increases, the temperature increases of the system, then at that when it attains the discharge pressure which is pH, the hydrogen is discharged and then it is being cooled. Then it is being cooled from 4 to 1 so that it attains the pressure which is lower after discharge, and at the same time the temperature of the bed also reduces. Now, this is a single stage compressor, but usually with a single stage compressor the final pressures attained, the delivery pressures attained are not very high. So, multi-stage compressors are required in which similar absorption and desorption cycle takes place, and that is successive absorption and desorption cycles takes place, but in several beds. These are matched in such a way that the low pressure hydride which desorbs at a temperature TH, that is in synchronization with the absorption of the next stage. So, the second stage will be superimposed and synchronized in such a manner that the desorption temperature of the first stage matches with the absorption temperature of the second stage. And in this way we can couple these stages together so as to achieve a multi-stage compression, and we can get the desired pressure ratio or the compression ratio. Now, what is desired in such metal hydride based compressors is we need to have an appropriate metal hydride, which is the key component, such that it should have the desired thermodynamic properties, the delta H, delta S values, it should have the required heat capacity, the kinetic properties, so as to have this compression having a better productivity, faster kinetics. We need to also design the different components of the compressor, and there should be different methods and accessories so as to supply the required amount of heat and remove the required amount of heat. Usually these metal hydrides, they have poor thermal conductivity. As such, we need to improve onto their thermal conductivity, or we need to have a better heat exchange surfaces involved so that the reaction does not stall. Now, usually when we talk about these metal hydride storage vessels or these tanks, these are tubular in nature, they could be cylindrical. So, if we consider a cylindrical metal hydride bed, in that case there is a central artery which carries hydrogen, and the annulus that has the metal hydride being stored, and there should be a heat exchange mechanism being integrated such that during the forward reaction when the metal hydride is being formed, when when metals are subjected to hydrogen pressure, in that case the heat which is formed in the metal hydride bed needs to be removed. At the same time, during the reverse reaction, when hydrogen needs to be desorbed, that amount of heat has to be supplied uniformly. So, for that a heat exchange mechanism need to be there. For more details we will study that when we will look at the metal hydride hydrogen storage systems design. Now, absorption takes place, and then when the required pressure we need to get the required pressure, desorption is carried out so that there is an increase in the pressure and finally we can get the desired pressure. Now, herein in the whole process a series of cooling and heating of metal hydride bed is done so as to achieve the compression, and that entire process is being controlled by the heat transfer. So, here heat exchange or thermal management plays an important role, and this heat transfer can be either by means of natural or forced convection. It can be either air cooled or it can be water. By the heat transfer fluid can be either air, it can be water, or it can be oil, depending upon what temperatures are desired. And with the help of multi-stage compression with a series of such coupled modules having metal hydride or such metal hydride beds with different equilibrium pressure at the same temperature, we can have incremental pressure between the different stages, or we can have progressive increase in the pressure with several such stages being added or in a multi-stage compression process. Now, metal hydride compressors, they have efficiencies like less than 25% at 423 Kelvin, but there are several losses also involved. The efficiency of these metal hydride compressors further reduces because there are several losses involved in the heat transfer. At the same time, during the desorption there is a heat transfer required, a heat requirement for the desorption, and for the cooling there again energy has to be supplied for cooling requirement to meet the cooling requirement. So, overall the efficiency reduces and it is at times less than even 10%. Now, the status is that HYSA systems, in South Africa they have developed several metal hydride based compressors, and these have been integrated for hydrogen refueling stations, which is used for fuel cell powered forklifts. There are several such demonstrations on these metal hydride based compressors. Now, if we look at the advantages of these metal hydride compressors, these are thermal driven devices. So, as such the waste heat from any a process heat or an industrial waste heat can be used to drive the process and improve the efficiency. There are no moving parts, as such they are compact and simple in design, but the major disadvantages are that an appropriate choice of alloy is required and a proper selection determines the efficiency of the process. The overall efficiency of compression is low because of the several losses as mentioned, and there is a requirement of efficient thermal management system for the removal as well as supplying the required heat of the reaction. So, to summarize, the non-mechanical compressors, they are more compact and simple in design compared to the mechanical compressors. They do not have moving parts, they are simple and compact, they have noise free operation, and they are much more safe and reliable. So, other than the metal hydride based compressors and the cryogenic compression we have seen today, there are electrochemical compressors, there are adsorption based compressors which we will learn in the next class. Thank you.